Today, we're pulling back the curtain on one of the most important but least understood parts of the Go build process, the linker. Think of it as the master architect. You write the code in all these different files, but the linker is what takes those scattered blueprints and assembles them into a single, solid structure that can actually run. We're going to demystify this whole process and give you a really solid mental model you can use every day. Okay, so to get started, let's use this super simple piece of Go code as our guide. I mean, it doesn't get much more basic than this, right? We've got a global variable x, a function add that just adds 1 to a number, and a main function that calls add and puts the result in x. You've written code like this 1,000 times. But the journey this code takes to become a running program is way more interesting than it looks. And that's really the heart of it. While this code is totally familiar, the process underneath is a bit of a black box for a lot of developers, especially that critical step called linking. Today, we're going to pry that box open. By the end of this explainer, you're not just going to know what the linker does, you'll get why it's so fundamental to how Go performs and how its tooling, like the debugger, even works. So here's our game plan. First, we'll nail down the linker's real job. Then, we'll dissect a Go binary to see how it's structured. After that, we'll get into the magic, how the linker turns names into actual memory addresses. This next part is huge. We'll talk about the linker's blind spot, the stuff it literally cannot see. Then we'll connect it all back to why this matters for performance and debugging. And finally, we'll see how the entire program comes together. All right, let's start at the beginning. What is the linker's true role? Well, in a nutshell, its job is to take a whole bunch of disconnected, compiled pieces of code that are full of placeholders and turn them into one single, cohesive plan that the operating system can actually execute. So here's the key thing to realize. By the time the linker gets involved, your Go code has already been compiled into machine instructions. But those instructions are incomplete. They're full of IOUs. They say things like, call the function named main.add, or put this value in a variable called main.x. The linker's job is to cache in all those IOUs. It replaces those names, which we call symbols, with actual hard-coded memory addresses. It's the one that decides exactly where every function and every global variable is going to live in the final program. Now, to make all those decisions, the linker needs an organizational blueprint. It can't just dump all your code and data into a file randomly. That would be total chaos and incredibly insecure. Instead, it carefully organizes everything into different sections, and each section has its own specific purpose and its own set of rules. So you might be asking, why even bother with sections? Well, it all comes down to a fundamental rule in computing, one that's enforced by the CPU itself. You have to keep your code separate from your data. Code is meant to be executed. Data is meant to be read and written. If you mix those two up, you open the door to all sorts of nasty security problems. This is how a lot of classic buffer overflow attacks work. These sections are the mechanism that enforces this separation, which lets the operating system set different permissions for different parts of your program. The first and maybe most important section is the text section. Now, don't let the name fool you. This has nothing to do with readable text. This is the raw machine code, the ones and zeros that your CPU actually understands. All of your functions, like main.add and main.main from our little example, they all live here. The operating system marks this part of memory as read-only, so your program can't accidentally change its own instructions while it's running. And of course, it's marked as executable, which is what tells the CPU, hey, it's safe to run the instructions you find at these addresses. Next up, we have a place for our global variables, and there are actually 2 sections for them. This is a really clever old-school optimization. First is the data section. This is for any global variable that you initialize with a specific value, like var message equals hello. That string hello has to be physically stored in the executable file, right? So it goes in the data section. But what about variables that are just initialized to their 0 value, like our var xint? Well, it would be a huge waste of disk space to store a bunch of zeros in the file. So for these, we use the BSS section. The BSS section isn't really a section at all. It's just a little piece of metadata. It's a note from the linker to the OS that says, hey, when you load this program, please set aside this much memory for me and just fill it with zeros. This makes our binaries a lot smaller. Then there's the RODATA section, which stands for read-only data. This is the perfect home for things that should never, ever change while your program is running. Things like string literals or other constants. By putting them here, the linker tells the operating system to mark this memory as read-only. This gives you a hardware-level guarantee that you can't accidentally overwrite a constant, which prevents a whole category of really tricky bugs. So this table is basically the mental cheat sheet you need. Think of it as the floor plan for your program. Text is for your code. You can run it, but you can't change it.
Data and BSS are for your global variables you can read and write to, and RODATA is for constants you can read but can't change. And just remember that key optimization. BSS is just metadata to save space on disk. It's a small detail, but it's why Go binaries can be so lean. Hey, before we continue, if you're finding this deep dive useful, you should definitely subscribe to our Gokun channel. We focus on Golang internals, architecture, and advanced execution flow concepts that you really don't find anywhere else on YouTube, and it's all completely free.
Okay, so we understand the layout of the building. Now let's watch the architect, the linker, actually place everything inside. This gets us to the absolute core of what the linker does, turning abstract names or symbols into concrete addresses. This is where the real magic happens. Before the linker does its thing, the machine code from the compiler is kind of abstract. An instruction doesn't say call the memory address 0x1000. Instead, it says call the function with the symbol main.add. It's just a name, a placeholder. Same thing for our global variable. The instruction is basically store this value at the location of the symbol main.x. It's like having a contact list with just names, but no phone numbers yet. And that brings us to the central question, right? The compiler is the one that creates these symbols, but it works on one package at a time. It has no clue where main.add is actually going to end up in the final program, which includes the runtime and all the other libraries. So how does the program bridge that gap from a simple name to a real numerical address that the CPU can actually use? The answer is the linker's methodical three-step process. First up is symbol resolution. The linker looks at all the compiled code from every package and builds a master list of all the symbols. It makes sure that every symbol that's being used actually exists, and, really importantly, that it only exists once. This is where you get those duplicate symbol errors. Second, address assignment. Now that it has the master list, the linker goes through and gives every single symbol a unique virtual address in the right section. Main.add gets an address in text, main.x gets one in BSS, and so on. Finally, and this is the most critical part, is relocation. The linker goes back through all of the machine code and essentially does a find and replace. It finds every placeholder like symbol main.add and patches it, overwriting it with the actual numerical address it just assigned. And this is the result. All those symbolic, human-friendly names are gone. The machine code is now concrete and self-contained. It now literally says, call address 0x1000 and store at address 0x2000. At this point, the CPU has everything it needs. It has no idea what add or x means. It only understands these numbers. The world of programming has been fully translated into the world of the machine. Now, we have to talk about a super important distinction here, virtual versus physical addresses. The addresses the linker assigns, like 0x1000, are virtual addresses. It's like your program gets its own private imaginary map of memory. Think of it like the linker assigns your function to apartment 401. When your program actually runs, the operating system acts like the building manager. It takes that virtual address and maps it to a physical address in the computer's actual RAM chips, something like building 7, floor 3, room 12. This whole translation happens automatically by the hardware, and it's what lets you run multiple programs at once without them stepping on each other's toes. So we've talked a lot about what the linker does see, functions and global variables that have a fixed location. But honestly, to really get this, the most important thing to understand is what the linker is completely, totally blind to. This slide right here, this is the key to the whole thing. On the left, you have the linker's world. It sees things that have a permanent static home in the executable file. Your functions, your globals, and your constants. It can give them an address because it knows they exist before the program even starts. But on the right, that's a whole world the linker knows nothing about. Why? Because none of it exists yet. Function parameters, local variables, return values, they all live on the stack. And the stack is a dynamic thing that's created at runtime, when your program is actually running. The same goes for the heap. Memory you get with make or new is requested from the OS at runtime. The linker did its job and went home long before any of that happens. It has zero knowledge of the stack or the heap. Okay, so who cares about this sharp divide between link time and runtime? Why is this architecture even important? Well, it's not just some academic detail. It directly affects two things that every single one of us cares about: how fast our code runs and how easy it is to debug when it breaks. First, let's talk speed. The reason a compiled language like Go is so fast is because the linker assigns these addresses ahead of time. It bakes the address of main.add right into the machine code as a call 0x1000 instruction. For the CPU, that is a single, super fast, direct jump. Now, imagine if we had to look up the address of main.add by its name every single time we called it. That would involve a slow dictionary-style lookup, which is basically how many interpreted languages work. By doing this work up front, the linker eliminates a massive amount of runtime overhead. And now for debugging. How do we get those nice, helpful stack traces when all the CPU knows about are raw memory addresses? Well, that's the other amazing gift from the linker. While it's working, it creates extra metadata tables. The most important one is called the pclntab, which stands for Program Counter Line Table. Think of it as a reverse dictionary. It maps memory addresses back to function names and line numbers. So when your program panics at address OX1000, the Go runtime catches it, looks up that address in the pclntab, and finds an entry that says, hey, that address belongs to main.add on line 5 of main.go. It then uses that to print the helpful error message we all know. Without that table from the linker, all you would see is panic at OX1000, which is completely useless. Okay, let's just zoom out one last time to see how the linker fits into the entire build process, especially when you're dealing with a real-world program with lots of packages and dependencies. This slide really shows the different scopes of the compiler and the linker. The compiler is a specialist. It works in isolation, one package at a time. It compiles your main package into an object file, main.o, and then it separately compiles the fmt package into fmt.o. They don't know about each other. The linker, on the other hand, is the master assembler. It gets handed all of the object files, yours, the standard libraries, the runtimes, and it looks at them all at once to build one giant global symbol table. It's the only one that can resolve the connection when your code calls fmt.println. And this shows the whole pipeline, start to finish. You write your .go source files. The compiler then translates each package into an intermediate .o object file, which contains the machine code and all its symbols. Then the linker steps in for that final crucial assembly step. It grabs all those separate .o files, resolves all the symbols between them, patches in all the final addresses, and stitches everything together into that single final executable binary that you can actually run. So if you remember just one single thing from all of this, let it be this. This is the mental model that locks it all in. The linker's world is static. It only knows about things that have a permanent home in the executable file, your functions and your global variables. The runtime's world is dynamic. It deals with things that are created on the fly while the program is running, local variables on the stack, and anything you allocate on the heap. Understanding that fundamental divide, that line in the sand, is the absolute key to reasoning about your Go program structure, its performance, and its behavior.